In this video, I'm going to work with one example of a power series before even defining what a power series is. In the next video, I will define power series in general, and I will state the main theorem about power series that makes them so useful. Here's the example. I want to define a function g with this equation, g of x equals this infinite sum. Notice that the terms of the sum depend on x. So in principle, for each value of x, I have a different sum, I get a different outcome, so this is a valid way to define a function. My question is, what is the domain of this function? Well, the domain of g will be the set of real numbers x such that this is well defined and actually produces a number. In other words, the set of real numbers x for which the series is convergent, because convergent means that the series adds up to a number. Without doing anything, looking just at the series, I notice that I have x to the n. So when x is a large number, the terms of the series are large, and probably I expect it to be divergent. But when x is a small number close to 0, the terms of the series are smaller, and probably I expect it to be convergent? Well, at this moment, I invite you to pause the video and try to answer the question and calculate exactly what the domain is. This is an exercise in convergence tests, and I suggest you begin by using the ratio test. Once you have done that, continue watching. I want to find all the values of x for which this series is convergent. There is one value of x I already know will work, when x equals 0. But let's see if there are others. I will begin by using the ratio test, because it is something I can try to use for all values of x at once. And for the purpose of the ratio test, I'm going to give a name to the terms I am adding. I will call them an. And now the ratio test tells me to compute the limit of the quotient of one term over the previous one in absolute values. And if this limit happens to be smaller than 1 or greater than 1, then we can conclude that the series is absolutely convergent or divergent. So let's write it down. As it is often the case with the ratio test, it is convenient to group similar terms with similar terms because they will simplify. And indeed, this simplifies. X to the n plus 1 over x to the n gives me x at the top. 3 to the n over 3 to the n plus 1 gives me 3 at the bottom. And then I also have the polynomials. And then in this final limit, for the purpose of the limit, x is a constant, so is 3. And the limit of n over n plus 1 is simply 1. So this limit ends up being the absolute value of x over 3. Okay, no surprise here, the answer depends on x. Now, if this limit is less than 1, the series is absolutely convergent, and if it's greater than 1, the series is divergent. This takes care of most values of x. Let's write it down. The best case is when the absolute value of x is smaller than 3, because in that case, the limit we just computed is less than 1. In that situation, the ratio test tells me that the series is absolutely convergent. The bad case is when the absolute value of x is greater than 3. In that case, the limit we just computed is greater than 1. And in this case, the ratio test also gives us an answer. The series is divergent. We still have to figure out what happens when the absolute value of x is 3. So when x equals 3 or minus 3. But so far we can draw a picture with what we have. We knew from the beginning the series is going to be convergent at 0, and in fact near 0, between minus 3 and 3, it is absolutely convergent. Then far away from 0, when x is greater than 3, it is divergent. When x is smaller than minus 3, it is divergent. And then we have these two boundary points where we don't know yet what is about to happen. 3 and minus 3 are two specific values, so let's write down what the series looks at those points and see what we can conclude. Conveniently, in both cases, the terms simplify quite a bit. 3 to the n over 3 to the n is 1. And here I separate the sign. And luckily, I recognize now these two series. The first one I know to be divergent is the harmonic series, or if you prefer, is a p-series with p equals 1. The second one is convergent, for example, by the alternating series test. The second one is convergent, but if I put absolute values on it, it would be divergent, so it's only conditionally convergent. So I now can complete this picture. At this endpoint, I get that it's conditionally convergent, and at this endpoint, I get that it is divergent. In the next video, I will define what a power series is in general, and I will explain that a situation like this one is what happens all the time. But to answer the original question, the domain of the function is the interval from -3 included to 3 not included. And we're going to call this domain the interval of convergence. And the radius of this domain, which is 3, we're going to call it the radius of convergence. For the definitions of these concepts in general, watch the next video.